I am super excited to talk to you about direct sequence spread spectrum, but before I do, I'm even more excited to begin this talk with a reading from POCR GTFO 3.2. There is an old name for what people do with big ideas and important concepts that are so important that you cannot hope to have their internal workings understood without special training by special people. It is called worshiping idols, and what we ought to do with idols is to smash them to bits. So the idol that I'm trying to smash today is direct sequence spread spectrum, which is a radio technology. And spread spectrum technologies are techniques that are used to have a radio system use more bandwidth than is actually necessary to transmit some information. And what we do with spread spectrum signals is the way spread spectrum signals work in general is that they kind of squander bandwidth in order to gain some other benefit. And some of the benefits gained tend to be immunity to noise and interference, which is a really useful benefit, but also people often tout benefits for security, like making signals difficult to detect, making signals difficult to intercept. And I'm trying to show today that some of these things are easier to detect and intercept and than you might otherwise think. So there are two major types of spread spectrum technologies, and those are frequency hopping spread spectrum, like is used in Bluetooth, and direct sequence spread spectrum, which is what I'm talking about today. And direct sequence spread spectrum tends to be misunderstood. When it was first explained to me years ago, it was explained completely wrong. So I'm going to take a little bit of time to kind of tell you how direct sequence spread spectrum works, and then we'll look at how to reverse engineer a DSSS signal. So if you transmit some bits, like in the upper left-hand graph there, I'm showing sort of a maybe a sequence of a 1 and then a 0 and then a 1 and another 1 or something like that. If you transmit some bits using any old modulation, that signal will use some amount of RF bandwidth, so some width in hertz over the air. If you transmit bits at a higher rate, like we do on the bottom, then the bandwidth of the signal will be wider. And the bandwidth in hertz is always going to be proportional to the bit rate. And so the trick that direct sequence spread spectrum uses is to inflate the number of bits per second with redundant information. And instead of calling these things bits, we call them chips. So a particular symbol that is transmitted, like mostly I'm going to be looking at binary phase shift key signals, so they're just two states, like a high state and a low state. But instead of having a high state be a 1 and a low state be a 0, you actually say a high state is just one of many chips, and you use a bunch of chips to send one bit of information. So like going across my graph paper here, I have a sequence of chips that's high, 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 low, 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 high, low, low, high, low. And these 11 chips actually represent one data bit. That's a 1. And if you want to transmit a data 0, you just transmit the inverse sequence of chips. So low, 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 high, 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 low, high, high, low, high. And what happens is you inflate your data rate from, say, 1 megabit per second to a data rate of 11 mega chips per second. And that increases the bandwidth of the signal by 11 times. And this is exactly the scheme that is used in Wi-Fi. Now, most Wi-Fi packets that you use are transmitting data at a higher rate than this, but the management frames, like beacons and probe requests and probe responses, are transmitted with this direct sequence spread spectrum scheme at 11 megabits per second. Or sorry, 1 megabit per second data rate, 11 mega chip per second chip rate. And the reason that this is so useful is because if the transmitter transmits data like this, the receiver can use correlation to detect the bits that were transmitted. So this is an example of correlation. If the signal across the top is what was received, and then in the middle there, I have the expected chip sequence, then the receiver can go through this process of correlation, which is a simple multiply accumulate algorithm. So we multiply in columns, starting on the left-hand side, the top, we call that a 1, and then the expected signal is a 1. And so 1 times 1 is 1. And then 1 times 1 is 1 in the next column. And then 1 times 1 is 1. And then -1 times -1 is 1. And so every single chip, if these line up perfectly, has a product of 1. And then you do the accumulate part, which is adding these 11 ones together, and the result is 11. So the result of this correlation of these two aligned signals is 11. But if you imagine that they were misaligned, then the result of a correlation would not be 11, because sometimes we'd get -1s down here. And you'd add up a bunch of 1s and -1s, and you're going to end up with a number somewhere near 0, like -1 or 1, something like that. And if you throw a bunch of noise or interference into the signal, you might blow away a chip or two, but you're likely to still have a correlation peak when these signals are aligned. So a receiver is able to recover the information that was transmitted by using this correlation algorithm, and the correlation over time will be near 0, near 0, near 0, and then a big spike, maybe 11 or near 11 when a 1 is transmitted, and then near 0, and then a low spike when a 0 is transmitted, and then back and forth. You'll see these spikes, and that's how a receiver is able to be relatively immune to noise and interference that otherwise would severely impact a system that doesn't use direct sequence spread spectrum. And this is, as I mentioned, used in 802.11. It's also used in Zigbee. It's used in GPS. If I remember correctly, the GPS sequence is 1,023 bits long, the chip sequence, and it's a pseudo-random sequence. And it's also used in a lot of proprietary systems, especially satellite communication. And this is where I think these systems are interesting from a reverse engineering standpoint. Sometimes you might want to, you might be interested in picking up a signal. You might not know what it is, but you can maybe detect a signal that people thought would be difficult to detect. And you can reverse engineer the chip sequence. Because if you know the chip sequence, then you can decode the transmission. But you need to have the chip sequence, which is a pseudo-random sequence. And these systems can be kind of buried in the noise. Supposedly they can be detected if they're even below the noise floor, although exactly what that means is a bit questionable. But you can definitely have a negative signal-to-noise ratio and have the ability to detect signals and decode them if they have a long enough chip sequence. The longer the chip sequence is, the more immune to noise and interference the signal will be. And it's relatively easy, however, to detect these things even without prior knowledge if you use certain techniques, like if you point a very high gain directional antenna at the transmitter, you're much more likely to be able to detect it. But you kind of have to know which way to point it. But it turns out we can just use some math instead. Math is great. It turns out it doesn't take very complicated math, which I'll show you shortly. I'm going to use as a target device the Spot Connect, which is a personal satellite communicator. It's a small device that lets you like transmit short messages, such as your latitude and longitude, through the Globalstar satellite system anywhere on Earth. And the first time I saw one of these was a signal that Travis Goodspeed sent me that I started trying to reverse engineer. Later, I've used it quite a bit in some of my training classes, but I've also, I want to point you to some work done by Colby Moore. He gave a talk at Black Hat a couple of years ago, in which he kind of reverse engineered this system a little bit more thoroughly and published a bunch of information on it. So if you want to know specifically about the global star system, go see his talk. What I'm going to show you is kind of techniques that go beyond what he was doing, not focusing on the spot connect itself or the global star system itself, but showing you techniques that can be used to reverse engineer any DSSS system, even in the presence of a lot of noise. So I'm going to use GNU Radio Companion here to kind of show you how these techniques work, and then I'm going to show you a command line tool that I just published yesterday that you can use to kind of do the job automatically for you. But GNU Radio Companion is super useful for kind of seeing how things work and fit together and experimenting with things. So I have this file source, which is just a capture file. I captured with a HackRF, captured a signal from a spot connect. And the flow graph as it is now, if you ignore all the stuff that's grayed out, the flow graph is pretty simple. I'm just throttling it to real time. I'm adding in some noise, but my noise amplitude is 0, so that's a NOP. And then I'm multiplying by a signal source, which is a way to shift the frequency, but I'm shifting the frequency by 0, so for now that's a NOP. And then I'm just visualizing the frequency sync, which is doing the FFT to show across. You can see how the width in hertz is of this signal that is appearing. You'll see it dip down every once in a while because this is a repeated transmission. So that big hump in the middle that occasionally goes away is the actual signal of interest. It's pretty close to being centered in my visible bandwidth, but not perfectly. I can add noise if I want using that top part of the flow graph and this slider. I can use this other slider to shift the frequency. And that's all I have so far. So the next thing I want to show you is how I could detect this signal. And this is a trick that I've seen done before. I think Balint Sieber was the first person I saw do this. And that is to multiply the signal by itself. In other words, I'm just squaring every sample. That's it. And then I'll run that through the FFT and take a look at the result here. So down here at the bottom, I have my original signal visualized. And then up here, I have the squared signal visualized. And you see how there are these very prominent peaks. It turns out that this peak, this highest peak, indicates the center frequency of the transmission. This is a characteristic you see in any BPSK, binary PSK, binary phase shift keying signal. And most direct sequence spread spectrum systems encode or modulate their chips with BPSK. So this indicates the center frequency, and then these two peaks on either side, these kind of pretty tall ones, actually indicate the chip rate. Why does this work? Well, first I'm going to actually see if I can shift the center frequency to 0 hertz, which could be handy. In fact, if I do this, if I zoom in, I could actually just detect that's at 0.474 megahertz or 474 kilohertz. That actually, if you move this slider, you'll see that this plot up top moves side to side twice as fast as the one below. Because since we squared the signal, that peak indicates twice the offset from center. So I'm going to put in that offset as my default value for that slider, 474 kilohertz divided by 2. And now it's nicely centered at 0. And this peak over here indicates my chip rate of my signal. It's 1.25 megachips per second. So why does this work? Well, if I bring in this constellation sync here, what the signal looked like before I squared it is something like this. And BPSK has these two constellation points. There's on opposite sides of the origin. So like sometimes it's transmitting a 1 and sometimes it's transmitting a -1. It's really kind of that simple. The only thing that's sort of complicated about it is that samples have two-dimensional quantities as opposed to being a one-dimensional quantity. But in BPSK, it's just two opposite points. It's jumping back and forth. And you'll see some intermediate points near the origin as it's going back and forth, but most of the samples are clustered around one side or the opposite side. Now, if we square the signal, you know, if you square a 1, you get a 1. And if you square a -1 on the opposite side, you get a 1. So if you square the signal, these two constellation points collapse together. And that's what happens if I put this multiply block back in and then run that through my constellation sync. So what happens here is now this is the origin, and this big blob is both my constellation points that have now been sort of collapsed to the same point. And so instead of jumping back and forth between opposite points pseudo-randomly, now it's jumping back and forth or back to the same point every time. Every time there's a symbol transition, it's sort of dipping toward the origin and then back to the constellation point. And that's exactly why we get a peak right here at 1.25 megahertz, because it's picking up the fact that we're swinging to the origin and back 1.25 million times per second. So now we know the chip rate. I can plug that in over here. And I'm going to show you another trick, and this is something that, well, actually, before I show you another trick, let me show you kind of the traditional way to reverse engineer this at this point, and I think this is what Kobe Moore did. He used a BPSK demodulator here. He needs to know the samples per chip, which is computed, here it is, computed from that chip rate and the sample rate. And now I can take this and just demodulate it. I don't need that squaring trick anymore. And here you can see at the top, these are the actual chips. And you can just read the chip sequence right out. Now this works great, but it only works well if you have a good signal to noise ratio. I have a good signal to noise ratio because I have the transmitter nearby. But what if you were trying to pick up a signal that was being transmitted from the satellite, not the signal that was being transmitted by a handheld device? And I would have a much worse signal to noise ratio. And if you start adding noise to this system, this technique totally breaks down. You can't just do a traditional BPSK demod to recover the chip sequence if you have a terrible signal to noise ratio. So I've been looking at ways to kind of continue this process of reverse engineering and actually recover the chip sequence, even in the face of a lot of noise and interference. And the next trick I want to show you is that I can delay the signal by the number of samples per chip, and then just subtract that delayed version from the non-delayed version. And if I do that, then I'm getting like a differential of like one chip versus the next chip. So I'm looking for chip transitions instead of the absolute value of a chip. Absolute value is really not the right word to use there. And then I'll just measure the magnitude of that result. I don't care about its phase, and visualize that in a time sync. And now you can see this looks a little bit similar, but slightly different, because what I have is a peak every time there is a transition, a chip transition. It's either going from 1 to -1, or it's going from -1 to 1, -1 to 1. I don't know which, but I don't really care which at this point. I just want to know, I want to know the timing of those transitions and be able to distinguish them from a time when there's no transition. And then what I like to do is institute another little delay, and this delay is by the the length of the entire chip sequence, the number of chips times the samples per chip. But I don't know the number of chips. So I'm just going to make a little slider here that is called num chips, and it started at 0. I'll enable this one. There we go. And so now I have actually two colors in this plot that are obscured by each other. I have a version that's delayed by my guess of the entire chip sequence length, and a version that's not delayed. And if I increase this number of chips, at 0, they are right on top of each other. But if I add a delay of 1 chip, you can see that red and blue are kind of off by 1, and I can keep increasing this until they line up again. It turns out this takes a while because this system has a chip sequence that is 255 chips long. And so if I just slide this over, if I'm at 254, you can see they don't line up. But if I'm at 255, they line up perfectly. And this works pretty well, and this is basically a visual way of doing an autocorrelation. I'm seeing the property of the system, how self-similar it is, and what periodicity that similarity has. And this is still somewhat prone to trouble if I add noise in. But this can easily be extended. For one thing, I could be properly using the autocorrelation algorithm instead of just visually doing this. But another thing I could do is I can do something slightly more sophisticated. This nonsense here is just a way of getting a 1 followed by a whole bunch of zeros followed by something else. If I put in my 255 chips in a sequence here, you can see the result. I'm taking 20 different repetitions and adding them all together. So the blue signal down at the bottom is just that first differential, just 1 chip sequence minus the previous chip sequence. But this red signal is 20 of those all added together. And now it's more immune to noise. This technique, you can see as I raise my noise slider, you can see that noise floor in the red signal raise up. And my immunity to noise here is proportional to how many repetitions I add up, which is super cool because all I have to do is just throw more CPU power at the problem to get more noise immunity. Really easy. And it doesn't matter if these chip sequences are inverted or not. Right? Some of these chips are representing a 1, and some of these chip sequences are representing a 0, so their entire sequence is inverted. But since I'm doing the differential, the chip differential is the same regardless of whether a 1 was transmitted or whether a 0 was transmitted. And so they stack up together because I'm doing the differential. And at this point, I can actually, well, right here, can actually, in theory, just like read these things, like read the chips. But I don't know like the starting value, right? It's either going to be, if I just guess a starting value, although I still have to somehow determine the start of the sequence, like when is the start of the sequence. So there is another way I can determine the start of the sequence. I do this thing where I, now that I know the length of the chip sequence, I'll go in here and delay by the number of chips times samples per chip. And now I have this thing that looks kind of messy, but if I trigger, you can see now I'm triggering on a transition from one entire chip sequence to another entire chip sequence. And this only happens, I only get this trigger, most of the time this value is really low because I'm getting like the same chip sequence in a row. But when I suddenly get a transition from one chip sequence to another chip sequence, I can now read the differential of the entire chip sequence right here. And I don't know whether it starts with a 1 or starts with a 0, but it doesn't really matter because I can fix that later if I have to. And this is a differential, but from that I can recover the chip sequence. So now I'm going to show you how this can be done using a little command line tool. that I just published yesterday. It's in my clock recovery repo, if you're interested, in GitHub, ossmann/clock recovery. And I'm going to take that exact same file and run it through this little Python program that kind of does more or less the same things I just showed you. It's a little slow, but here we go. It corrected our frequency offset, and this is in units. This is a ratio. It's taking 1 million samples, and it's computing this ratio of 1 million. And then it's detected a chip rate, which is 250,000 over 1 million. So it's 1/4 of the sample rate. And my sample rate was 5 megahertz. So 1/4 of the sample rate is, in fact, 1.25 megachips per second, which is exactly what we determined in GNU Radio Companion. Notice there is a 2 parts per million error detected here. That's likely an actual clock offset in a crystal error in either the target device or my HackRF or some combination of those two. But I can measure that quite precisely. It detected automatically my chip sequence length, again using more or less the same technique that I showed, except I think it's actually using the autocorrelation algorithm. And then it's dumping out the chip sequence. So here's my chip sequence that I can use to now correlate with the signal and start decoding transmissions and know exactly what bits were transmitted. And I don't know for sure whether this should be starting with 8 ones or it should be starting with 8 zeros, but it doesn't really matter because later on I can just invert all bits. And in fact, BPSK by its very nature has an ambiguity. So even a legitimate receiver might not know whether it starts with a 1 or a 0. But actually chip sequences are one way that receivers can figure that out. So this is a little tool, and let me show you, I can do the same thing adding some noise into it. This is kind of slow because it's doing million bin FFTs and several million bin FFTs, which is kind of ridiculous maybe, but you know, I'm not going for speed here. I'm going for ease of use and having it just work and reverse engineer stuff for you. And you'll see I got the exact same chip sequence with a little bit of noise added in. It doesn't work as well as I thought it would with a lot of noise added in, but let me show you where it fails. It detected the signal, it detected the frequency offset, it corrected the frequency offset, it detected the chip rate correctly, but then it failed to detect the chip sequence length and failed to, of course, get the chip sequence because it was looking for something that was only 1 long, which is like nothing. So, so there's a little bit of work that could be done probably to improve this and make it work even better with more noise. But just to give you an idea of how much noise there was here, it did partially reverse some information about it. If we look at the original signal, it had a signal to noise ratio. Wait, is that? No. Let me show you. Let me show you the original signal first. The original signal had a really nice signal to noise ratio, something that looks like this, and the signal with all that noise added in looks like this, and you really can't see the signal of interest at all. It's totally buried in the noise visually, but we're still able to recover at least some information about it. And I think with a little bit of improvement, I should be able to get this fully automated chip sequence analysis to work, even in the face of a whole bunch of noise and interference. So to summarize, direct sequence spread spectrum signals are pretty cool. They tend to be really immune to noise and interference, but they also tend to be touted as ways to make signals difficult to detect and difficult to intercept. And it turns out doing very little bits of math like squaring or subtracting, turns out that tiny little bits of math are enough to make it entirely possible to blindly reverse engineer these things and detect them. Thank you very much. Any questions? We have one over here.
Do you have an upper bound on chip sequence length you've tested against or expect it to work with this technique?
Good question. Is there an upper bound on chip sequence length? I would say no. The only problem with adding more chips is that you require more CPU and memory to analyze them. But in practice, I don't think I've ever seen a system that uses more than a few thousand chips. And that is totally easy to do on modern computers.
There are practical systems that use hundreds of millions.
Hundreds of millions?
Yeah.
I have no reason to expect that this technique would fail to work, other than that it would be slower. Yeah.
Okay, thank you.
Anyone else? It's your last chance for the entire con to ask a question. All right, there it is.
Hey, thanks. It was a great talk. I guess I'm not super familiar with this kind of thing. So my question is it merely uncommon or impossible for the sequences for 1 and 0s to be in? Can they not be inverses? Is that just an implementation detail they usually are, or is it impossible to implement this kind of a thing and not have them be opposites?
So you might have some kind of a system where they're not inverse. If you had, let's say, a quaternary spreading sequence instead of a binary spreading sequence. I'm not sure I know a practical implementation of that, but in theory, you could have a spreading sequence that consists of multiple points around the unit circle in the complex plane, and they don't have to be two opposite points, but they probably should be equally spread around the unit circle.
And you could adapt the technique then fairly easily to accommodate that, couldn't you?
Yeah. Instead of doing a subtraction here, I would probably do a divide or a multiplication by a complex conjugate. Why that works is left as an exercise to the reader. But in general, this type of technique where, oh, you're not seeing my screen anyway. In general, this type of technique can be adapted to such systems, as long as the key thing is that you find some way to create a differential of the chip sequence, as opposed to trying to get the particular constellation point of the chip.
Yep.
If that makes sense. All right, thank you all very much.